Good day, I'm Len Patrick Garces from the University of South Australia, and I'm here to talk about the put-call transformation for the exchange option problem under stochastic volatility and jump diffusion dynamics. This is joint work with my PhD supervisor, Gerald Chang, also from the University of South Australia. So exchange options are financial contracts which give the holder the right, but not the obligation, to exchange one risky asset for another. So for the European exchange option case, the payoff at time t is given by this function here. And in the context of the American exchange option, Wierskund and Stensland introduced the term put-call transformation, which involves selecting one of the assets as the numeraire and then factoring that out and establishing an equivalence to an ordinary call or put option on the ratio of the two assets. So this technique relies on the homogeneity of the payoff function and requires us to define an equivalent Martingale measure where one of the risky assets is the numeraire. So it's not particularly new. It's also called the dual market measure, and it was used by Margrab to price European exchange options. And it has also been used to price European exchange options in the Levy process setting, as well as the stochastic volatility setting. What we want to do in this presentation is combine those two. So what happens if the asset has jumps and stochastic volatility? Let's see what the put-call transformation method gives us. Other existing work on exchange options are as follows. So this is for the European exchange option case and for the American exchange option case. So just to differentiate between our earlier work, we will actually use here, the put-call transformation as opposed to the usual risk-neutral approach where the money market account is used as the numeraire. So just a quick list of our contributions. We apply the put-call transformation technique to when the assets are driven by SVJD dynamics. And we also would like to discuss a little bit about the American exchange option, finite maturity American exchange option, and its early exercise features. And I'll just outline these. The third contribution, the derivation of integral representations as we proceed. Further details are shown in our archive preprint. Now, we assume that we are on a probability space which supports three Wiener processes, correlated Wiener processes, two Poisson random measures, which are independent of each other and of the Wiener processes. We also consider a finite time horizon t, and the filtration generated by B and NJ satisfying the usual conditions. Now we assume that the market has two risky assets, S1 and S2, driven by the usual Bates stochastic volatility and jump diffusion dynamics. The volatility itself is driven by a CIR type process. And we have a risk-free asset or money market account, which has deterministic dynamics. We assume that the variance satisfies the Feller condition so that it remains strictly positive in any probability measure that we shall consider. And to characterize that probability measure, we need a Radon-Nikodym derivative process, which is parameterized by three adapted processes and four constants. And it has this form here. We assume that it's a Martingale and it has expected value equal to 1 at time t. And with this specification of the Radon-Nikodym derivative, we can define a Q hat Wiener process or Brownian motion, and we can consider the new intensity and moment generating functions of the jump intensity and the jump size random variables. Now, what we want to do is use the second asset yield ratio as second asset yield process as the numeraire, and define Q hat to be the measure under which the asset yield ratio, so the quotient between the yields of the first and second assets, and the discounted money market account, we require them to be martingales under Q hat. And that happens if we choose the parameters as follows, okay? To preserve the time homogeneity of the jump part, we assume that the parameters associated with the jumps are constant. And under Q hat, we now find that the asset yield ratio S tilde and the variance process evolve according to these equations here. So the asset yield inherits the jumps in the first and second asset prices. And we have the same CIR type structure for the variance process with the modified parameters. Now, at this point, we are ready to derive the European exchange option, the pricing IPDEs, the integral partial differential equations. And with some manipulation, we can actually reduce the payoffs to something that depends only on the asset yield ratio. And under the no arbitrage assumption, this has to satisfy, or the discounted European exchange option price has to satisfy equation 10 here. And since the only variable at this point is S tilde, we can actually make the alternate representation V tilde, which is given by that conditional expectation here. So at this point, we see that the pricing problem is equivalent to a European call option, okay, on the asset yield ratio. And to derive the IPDE for V, we require that it is twice differentiable in the S tilde and V variables and differentiable in T with continuous partial derivatives. And the IPDE is shown here. It satisfies equation 13 and 14, the terminal value problem, where the operator LSV is the one induced by our asset price dynamics. And this representation can be derived using the usual Martingale arguments and Ito stochastic calculus. We can also do the same for the American exchange option. So we can express the discounted American exchange option price as this essential supremum of an expectation using our usual optimal stopping arguments. And associated to this are some continuation and stopping regions, which we denote by calligraphy C and calligraphy S, which divide the domain, where you exercise if it falls in the stopping region, and you don't exercise the option when it's still in the continuation region. We call this BTV, okay, the early exercise boundary, and it's known that in the continuation region, the American option behaves similar to the European option. So we have the same IPDE for the continuation region. But to make sure that the surface, the pricing surface, is continuous across the stopping and continuation regions, we require a value matching condition and these smooth pasting conditions. So these conditions augmented to the IPDE from before gives us the complete picture for the American exchange option price. Of particular interest is the limit of the early exercise boundary at maturity, which is given by this proposition here. So we know that at time t, it's equal to 1, but as time approaches maturity, we actually have this limit here, which is an implicit equation dependent on the dividend yields as well as the jump parameters. Now, the main idea here is that because there are jumps, the investor tends to exercise for a higher asset yield ratio in fear of losses due to sudden jumps that occur upon exercise. So what happens here, we can prove this using arguments by Chiarella and Diogas for an inhomogeneous version of the IPDEs that we derived in the previous section. And the continuity condition for this is given by this proposition here. So if the dividend yield for asset one is high enough, then the boundary is actually continuous. We can verify this proposition numerically by assuming that the jumps are normally distributed, sorry. Here we have the curves are the right-hand sides of the implicit part. The 45-degree line is the identity. So when the curve intersects the 45-degree line, that's where your solution is for the implicit part. And we want to monitor whether that is above or below 1. So here we have small values for Q1 corresponding to limits which are higher than 1, or solutions which are higher than 1. In fact, we are not able to calculate the boundary if Q1 equals 0. But if Q1 is high enough, then the intersections actually fall below unity, which imply a continuous early exercise boundary. So now that we've simplified the exchange option pricing problem to a one-dimensional problem using the put-call transformation, what's next? It turns out that we can solve for integral representations of the exchange option prices using the joint transition density function of S tilde and V. And once we've derived the backward equation for that transition density function, we can then solve it using Fourier and Laplace integral transforms as done by Chang et al. For American call options under SVJD dynamics. The details of that are found in our archive paper. And then after that, what's next? We can evaluate those integral representations using numerical integration. And if we consider the IPDEs themselves, we can employ numerical methods to solve those. In fact, the next part of my work is working on an implementation of the method of lines to solve the IPDE arising from the put-call transformation. So that concludes my presentation. I thank the UniSA and Ateneo de Manila University for their support. These are some of my references. And thank you very much. If you're interested, our paper can be found on archive, and I hope to see you during the live discussion.